Hello everyone, this is part 2 of section 15.1 double integrals. Last time we left off with a couple examples of just evaluating double integrals, but as we had mentioned on the first page of notes, basically we can think of these double integrals as being volume, where the function f of xy is the surface z, and if we're talking about a rectangular region and we let z be equal to 1, then the integrals either become, depending on how you want to write your differential of area, either dy dx or dx dy, because you have 1 as your function, and your corresponding limits of integration. So what they would represent is both either the area of the rectangular region, or you can think of it as the volume of a rectangular prism, but with a height of 1, and that's because we're letting z be equal to 1. So you could actually, if you see the situation, you could actually just take the difference between the limits of integration for each variable and just multiply those differences together. But if you want to go through this formally, okay, first we'll integrate with respect to y, so we'll have the integral from 0 to 5 of y evaluated as y goes from 0 to 10. And then that would be with respect to x. So this is showing it formally because the integral of 1 with respect to y is y. Okay, now the fundamental theorem of calculus, so the integral from 0 to 5 of upper limit goes in, so 10 minus lower limit 0, and that's with respect to x. So there's that difference I was talking about between the limits of integration. So now this is just the integral from 0 to 5 of 10 with respect to x, which would be 10x evaluated from 0 to 5. And you could have said x equals 0, x equals 5, but really no need. So that's upper limit goes in 10 times 5, minus lower limit goes in 10 times 0, or 10 times 5, or 50. So you can see that it is the same as what I was talking about. Difference limits here is 10, difference limits here is 5, 10 times 5 is 50, and that's going to be your result. Then as an interpretation, once again, one of two things: either the area, think of the xy plane, and the fact that we went from 0 to 10 in the y, and 0 to 5 in the x. And so that area, of course, just base times height, 5 times 10. Or you could actually think of it as a volume. So here's x, here's y, here's z, and I don't know my scale, let's say x went out to 5. So let me call that one 5. And y is going out to 10. And so you'd have that rectangular region there. But then this is z. Z is equal to 1. So it's really just the rectangular prism, or the box, okay, and then that gives you the volume of the box, and that's volume is length times width times height, or 5 times 10 times 1, or 50. Over here I probably should have said area, base times height, or 10 times 5, or 50. Okay, so kind of interesting to see those situations and interpretations. It doesn't matter where you start. Here was 3 to 5, or excuse me, 2 to 5 and 3 to 6. Just keep in mind 2 to 5 is with respect to x, and 3 to 6 is with respect to y. If you wanted to draw this, let's just do the xy plane. We won't bother with the volume. But if you wanted to draw the rectangular region, which we often will be doing, now we're saying x is going from 2, say here, to 5, and y is going from 3, say here, to 6. So then we're talking about this rectangular region in here. And you can see the base is 3 and the height is 3. So looks like we're going to expect to get 9 out of this one. So let's see if we do it formally. And again, you could just take those differences like we talked about moments ago. But doing it formally, integral 3 to 6, integrate the differential dx, 1 dx that is, we get x, evaluated as x goes from 2 to 5, but then that integrated with respect to y. So that's the integral from 3 to 6. Upper limit goes in, so that's 5, minus lower limit goes in 2 with respect to y. So that's the integral from 3 to 6 of 3 with respect to y, which would be 3y, evaluated from 3 to 6, and then upper limit goes in, so 3 times 6, minus lower limit goes in, 3 times 3, so there's 18 minus 9, or 9, as we had expected. Okay, so rectangular regions are important, and if we evaluate a double integral over a rectangular region, it gives us the volume under the graph of the surface z equaling f of xy. So this first one, I think we'll just grind it out. We'll do the calculus. I'm not going to sketch it. It's kind of this one's kind of tedious to sketch, but the second one actually we can sketch that rather neatly. But for the first example, the surface is x plus y, and we're integrating over this rectangular region from 0 to 3, and then 0 to 2. So, showing the calculations, okay, I'm going to choose to use the brackets again. So whenever it's a little bit, when this is a function, if it's just a constant 1 like the last examples, no need really for the brackets, but you could use them if you like. But here I'm going to use the brackets. Integrating with respect to y, x is a constant, so that would be xy. And use parentheses around these as well. Xy minus, plus, integrating y, we get y squared over 2. Okay, and that's evaluated as y goes from 0 to 3. Close up the brackets. And then with respect to x. So then we get, by the fundamental theorem of calculus, integral from 0 to 2. Okay, I'll keep the brackets. Upper limit, 3 goes in for y. So 3x plus 9 halves. And then minus lower limit, 0 goes in for y. So that's just going to be a big 0. Because notice that y is a factor of each of the terms. And that's with respect to x. Okay, so this then gives us, just rewrite the integral from 0 to 2 of, now we have 3x plus 9 halves with respect to x. So integrating, get 3x squared over 2, or I'll write 3 halves x squared, plus integrating 9 halves, we get 9 halves x, and that's evaluated as x goes from 0 to 2. And again, there's really no need to say x equals 0, x equals 2, because that's the only variable left. So then fundamental theorem of calculus, okay, 2 goes in for x, so that's 4. 2 goes into 4 twice, 2 times 3 is 6, minus lower limit goes in, which is a 2, so 6 plus the 2's cancel, we get 9, minus, then the upper, I'm sorry, I think I misspoke there. I meant upper limit goes in first, and those are the calculations I just did. Now lower limit goes in, and lower limit is 0, and if x is 0, each of these terms go to 0, so we just get a big 0, and that would be 15. Okay, so here, volume of the z equaling 10x over that region from 0 to 5. Yeah, I got something going on here. Sorry, my computer was updating. I hope it didn't ruin this video. Okay, so this one we'll actually be able to sketch. If you consider the region from 3, x equaling 3, y equaling 5. That's the rectangular region we're talking about. Now, z is 10x, so when x is 1, let me label these 10, 20, and 30, because when x is 1, you gotta imagine this coming out, out of the paper at you. When x is 1, z is 10. And when x is 2, z is 20. When x is 3, z is 30. So this is coming out of the paper at us and forming that little triangular piece with the x-axis at x equaling 3. So we basically would have a mirror image of that here, little triangular piece. See, because y can be anything it wants to be, and that would be like a little triangular wedge. And if you didn't have these regions, it would go on and on forever, in each direction. But that's kind of a nice sketch of what we are calculating, the volume we're calculating. So in any event, the volume is going to be equal to the integral from, okay, we typically take, I neglected to mention this, the first region is always the x region. So 0 less than x, less than or equal to x, less than or equal to 3. And the second region, when it's given using this notation, I kind of assumed you saw this notation before, but I don't think we did. And the second region is with respect to y. So depending on how you set this up, okay, it's definitely going to be 10x here. And then it's actually your choice. It doesn't really matter what order you put this in. You could put the x first and the y second, or the y first and the x second, the differentials, I mean. So let me go with x's. So let me say dx dy. And then I'll fill in the limits. And the limits then, with this situation, the inner integral would be 0 to 3, and the outer integral would be 0 to 5, because the inner integral is with respect to x, which is 0 to 3 again, and the outer integral is with respect to y, which is 0 to 5. Okay, so then it's just a matter of evaluating this integral. This one's easy to do. Just integrate 10x, we get 10x squared over 2, or 5x squared. Evaluated as x goes from 0 to 3. I'll write x, literally x equals 0, x equals 3 in here. And then continuing fundamental theorem of calculus. Upper limit goes in, so 0 to 5 of upper limit 5 times 3 squared minus lower limit 5 times 0 squared. With respect to y, I forgot my dy over here. Put a little tally mark on the board. Pit of misery. Okay, so that's 945. So we get integral 0 to 5 of 45 with respect to y. And integrating 45 with respect to y, we just get 45y. Evaluated from 0 to 5. And upper limit, 45 times 5. Minus lower limit, 45 times 0. And that looks like it's 225. Okay, now the interesting thing here is that geometrically, if you look at the base, the rectangular region, that is 15 units, 15 square units, because you got x is 3 and y is 5. So that's area there is 15. And the triangle, actually I should have done it this way. I should have thought of looking at the triangular region. Let me get rid of that because that's not the... That's not gonna help in my geometric discussion of this volume. If we look at the rectangular or the triangular region, we have a height of 10, perpendicular height of 10 here, and the base is 3. So area of that triangle is 1/2 base times height, or 1/2 of 30, or 15. And then, I'm sorry, the height was 30. So that's 1/2 of 90, or 45. And then that 45, the triangular portion, is translated through an area, a distance in the y direction of 5 units. So then we've got the volume to be the area of the triangle, 45, times the change in y, which is 5, which is 225. Okay, so kind of neat to show the verification there, but not really necessary. But you could obviously imagine more complicated functions, very powerful to be able to find the volume that way. Okay, so we've got one more concept to finish up in section 15.1. I think we'll come back and do that next time, so we'll see you when you are ready.